Hi everyone, this is Derek Burkhart.
And Mike Scheller.
We are Team Rolling Freedom, and this is our video project on the Large Binocular Telescope, also known as the LBT. The Large Binocular Telescope Observatory is located in southeastern Arizona, near Safford in the Pinalino Mountains on Emerald Peak at an altitude of 3,200 meters. This area is part of the Coronado National Forest. LBTO is headquartered on the Tucson campus of the University of Arizona. On the LBT, there are two primary mirrors separated by 14.4 meters center to center and provide an interferometric baseline of 22.8 meters edge to edge. The binocular design, combined with integrated adaptive optics utilizing adaptive Gregorian secondary mirrors to compensate for atmospheric phase errors, provide a large effective aperture, high angular resolution, low thermal background, and exceptional sensitivity for the detection of faint objects. This is demonstrated by the slide here, where the light passes through spots 1 through 5. The light source enters the main mirror and reflects into the secondary mirrors, where the resolution is kept high for the images produced.
We're sitting here with Dan Pappalardo with the Ohio State University Astronomy Department and his involvement in Ohio State's involvement with the Large Binocular Telescope. Dan, would you mind talking about your involvement with the Large Binocular Telescope?
Well, OSU is one of the partners of the telescope, which means that our astronomers get to use a fraction of the time on the telescope. Ohio State is approximately 1/6 partners of the telescope. From my point of view as an engineer working for the department and the laboratory that I work for, the two main involvements we've had with the Large Binocular Telescope has been one, to build a coating system to put aluminum on the primary mirrors. LBT has two 8.5 meter primary mirrors, and we developed and built a system to deposit aluminum on those two mirrors. After that, our next contribution was to build a large spectrograph for each side of the telescope, so two copies of a multi-object spectrograph called MODS, and we have delivered both copies to the telescope. One is working, and one has been fully commissioned, and the other one will be commissioned soon.
What has made the LBT a unique telescope to work on or to be involved with?
Well, we can focus on one aspect of it was our recoding system, which one novel thing about that was that we decided to make a design that would illuminize recoat the mirrors on the telescope. Most telescopes, the mirror is removed from the telescope and either brought down to a different building or shipped somewhere to be recoated. The system that we built includes a bell jar which goes right up to the telescope, and the whole process happens right on the telescope. So that's one novel feature of that telescope. The fact that there's two mirrors has us on a schedule right now of doing one each year. So the current schedule has a coating lasting 2 years because we alternate recoating the different sides.
With this unique process to this telescope, has this helped aid in other telescope processes as far as their recoating or any involvement that way?
We have not had any offers to do our system for other telescopes. The closest similar telescope is the GMT, the Giant Magellan Telescope, that uses 8.4 meter segments, but I believe they will be removing the mirrors off the telescope to be done in a building.
You touched on this a little bit earlier, but what has been then OSU's continued involvement with the telescope?
Well, right now, as I said, with the spectrographs that we delivered there, MODS 1 is fully commissioned and operational, and MODS 2 is close to completing its commissioning. So that will complete our first round instruments that we're building for the telescope. And then when those are complete, we'll look to the second set, which has not been defined yet.
All right. Well, thank you very much for your time today.
You're welcome.
With the LBT, these images have been captured. These show what the LBT is capable of and how it can help find exoplanets and the possibility of life. This image shows the blue shift with the telescope. This image shows the powers of the red shift. This image shows a system that is one of the key images from the telescope, with a view of 4 young stars in the Orion Trapezium cluster, 1,350 light-years away, as seen through the LBT's adaptive optics. This is the best image ever taken of these stars, which are all tightly located within 1 arcsecond of each other. The movements show that the mini-cluster of young stars were born together, but will likely fall apart as the stars age and interact with each other. As we search for the possibility of life in the universe, the LBT helps us now and into the future. The LBT has been key on focusing in on star clusters that were unviewable before. We are now able to look deeper into those clusters and search for life.